Begin with. So our next speaker is Claudio Lazarte. I hope I didn't mangle your name too badly. Who's going to talk about dynamical stability and formation of multi-field Proca stars. So Claudio?
Yes, thank you very much. It's a pleasure to me to be part of this North American Einstein Toolkit Workshop 2024. I'm Claudio Lazarte, first year PhD student of the Department of Astronomy and Astrophysics from the University of Valencia. Today I'm going to try to show some of my first results of one of my main projects in my PhD program. I currently working with Nicolás Sánchez Gual and José Antonio Font. They are my current PhD advisors. And this work also has the contribution of Miguel Cubierre, that was my former advisor in my master program in Mexico, and Gabriele Paloni, that is a PhD student also in University of Valencia working in bosonic star researches. So just to introduce the main ideas and why we are studying Proca stars and even multi-field Proca stars, let me just mention that a simple definition for Proca stars. Proca stars are stationary classical solutions for cell gravitative configurations made of massive complex vector bosonic fields. In this talk and in the references, you can find them as Proca fields. And since the matter content is given by these bosonic fields, these Proca stars are classified as bosonic stars along its scalar cousins, known as well as scalar boson stars. We can find in the reference different motivation, but the two main that I found interesting are one that comes from cosmology, because Proca stars could be considered like dark matter candidates. For example, hypothetical primordial black holes from, primordial dark vector bosons coming from the early universe would condensate into Proca star and survive as a significant component of dark matter. This is a study that Marco Gorgetto presented, for example, in 2022. There is a astrophysical motivation as well. These Proca stars arise as simple models of dynamical stable exotic compact objects, and could also be seen as black hole mimickers. So that offers an alternative to the interpretation of strong gravity data against the black hole paradigm. For example, in 2021, Juan Carlos Bustillo and collaborators of the University of Valencia shows that the gravitational wave signal 190521 is consistent with a merger of a Proca star. Okay. And why we are studying Proca star made of multi-fields or made of several fields? In this case, we found the motivation in quantum physics. In 2023, Miguel Alcubierre and collaborators of the University of Mexico found that, using basically the semi-classical approximation of gravity in quantum field theory, they found that just with a single quantum zero spin field and its distribution of excitations, they can form the same space, they can source the same space-time for a classical multi-field boson star. So that is basically the motivation to study multi-field bosonic stars. They did that for an scalar, for the scalar case, but we would like to extend to the vector case. So in this case, we try to work with the classical regime of multi-field vector stars or Proca stars, and then see if exists quantum content part for this kind of systems. For example, these ideas, well found interesting in the Science Focus magazine from BBC, and they present, for example, a little bit about these bosonic stars, where they named them as dark stars. Okay, to begin with the questions. The first equation I want to show you is the action of the Einstein multi-Proca system. We can recognize here the Einstein gravity, and for the matter content, we will have n complex Proca fields. This part is basically the action of the electromagnetism, but in this case with a mass term and a mass value of the bosonic particles given by the mu parameter. And we will just focus on studying equilibrium configurations for spherically symmetric spacetimes. In that sense, we could have several fields, and we don't need to impose the spherical symmetry in those fields. But when they couple gravitationally, they have to form a stress energy tensor, a total stress energy tensor that has the symmetry that we want. I mean the spherical symmetry. The case with n equal to 1 for just one field is the case that was presented in 2016 for Brito and collaborators, and is the standard ansatz for the Proca star. What we did first was extend this ansatz for a case, a more general case, using 2L plus 1 fields, where L is the angular momentum number associated in the spherical harmonics that we can see here. And M is a parameter that goes from minus L to L and is also present in the spherical harmonics. Here, what we have is an ansatz for several fields. Each field is labeled with the value of the M, and those fields couple gravitationally in such a way that they produce a total stress energy tensor that is spherical symmetry, and satisfies the Gauss constraints as well. That's why this ansatz has this form. We can see quickly the harmonic time dependency that is characteristic for these bosonic stars. Also the scalar potential, but in our ansatz, we multiply by the spherical harmonic given the angular dependency. And the three-vector potential in our case is a little bit more complex than the case for n equal to 1. We had to put another radial function here, the B function, and also the angular dependency for the polar and the azimuthal components of this vector are given by angular derivative of the spherical harmonics. And as I mentioned before, this form of these ansatz satisfy the constraints equation, and that's why we found that is the appropriate ansatz for this generalization. As the parameter L is present in this ansatz and plays an important role, we call this system as L Proca stars, and they arise as the generalization in the spherical symmetry for multi-field Proca stars, basically. We present these results in a paper this year in 2024. Okay. Some interesting features about this solution that can also give us more idea about the bosonic stars are plotting in these profiles, in these radial profiles, where we can see the different profiles for different values of L from 0 to 3. We basically solve, well, we basically obtain these solutions solving a system formed by the equation of motions of the Proca field, the Hamiltonian constraint equation written in isotropic coordinates, and the second ADM equation for static space-time. We use a multi-domain collocation spectral code that I had the chance or the opportunity to present in the former Einstein Toolkit meeting in Europe the last year. We are happy to show that the multi-domain collocation spectral code works, and we already have the solution for the L Proca stars. We solve this system. Basically, the first 5 functions, F, A, B, alpha, and C are the variable functions of the system, but I also present the energy density here to watch basically that the space-time is regular in this case as the metric functions. Another characteristic that we can see here is that, for example, as we expect, the matter functions decays rapidly for large values of the radial coordinate. It's everywhere regular in the metric functions and also in the matter content given by the energy density. For the case of the metric functions, approach 1 more slowly as we expect as well. And the energy density in this case could give us some ideas about the morphology of these stars. For example, is spherical for L equals 0 and 1, and spherical has an spherical shell shape for L greater than 1. I think that the main interesting feature of this system is appears when we analyze the case L equal to 1. Mathematically, this is correct, the solution that we obtain. We also solve these equations using an approximation close to the origin to solve the equations analytically, and then numerically using the spectral code. But in this case, what we found was that the A function, when we have the value at the origin, the A function takes a constant value. And mathematically, this is not a problem, but if we try to interpret these systems as a physical system, these functions is the radial component, is the radial, well, this function give us the radial dependency of the radial component of the three-vector potential that I wrote here, for example. As in the origin, this value, this A, is not 0. What we have at the end is a multi-value vector function that is introducing this multi-value character due to the angular dependency given by the spherical harmonic for L equal to 1. So in this case, we basically have a lack of regularity due to the matter content. This analysis rules out the solution for L equal to 1. So in the next slide, I will just focus in solutions that rules out this case. Okay. Well, let's go with the dynamical stability. Well, these systems, basically the solution I already showed. Are solutions of the equilibrium equations, but those are not enough to say that they represent astrophysical objects. We need to determine this astrophysical viability doing some tests. One of them is, for example, the dynamical stability. Another could be a mechanism of formation proposed in the universe. We will first focus on the dynamical stability. And one could think that the simplest thing will be first begin with 1D simulations, right? But some previous studies about stability analysis show that when people study Proca stars with L equal to 0, that are the standard Proca stars in spherical symmetry, those systems are unstable when they evolve them in 3D simulations without imposing any symmetry. And that was a last result of Carlos Herderio and collaborators. That was a surprise because everyone everyone were thinking that the zero Proca star are stable, and that analysis was done using just 1D simulations with radial perturbations. But they found that not, but they found that when they put a zero Proca star in a 3D grid and evolve, then the system lose the spherical symmetry and migrate to a prolate configuration. For example, these points that are in the black line migrate to the points to the red line, and these lines represent the solution space for, in the case of the black line, for the spherical Proca stars, and in the case of the red line for the prolate Proca stars. Both stars are stars with the m parameter equal to 0, but with a different parameter of L. In this case, the monopole or the spherical is L equal to 0, and the dipole is L equal to 1. So with these previous studies, we decide to go straight to 3D numerical evolutions. So what we basically did was perform one of the standard procedures, that is the 3+1 decomposition of the spacetime and the matter variables, and using appropriate folation of the space-time, we could obtain by projections the scalar potential, the vector potential, an electric field, and a vector field for the Proca electromagnetism. However, this magnetic field could be computed from this expression, this the rotational of the vector potential that comes or that is equivalent to the Gauss constraint. So in our approach, we won't consider it as a dynamical function. So we will just evolve the three remaining fields. Okay, so for this simulation, what we did was using the Einstein Toolkit code. We had to modify a little bit the Proca torn that was already modified by Nico Sanchez Wall. But in this case, we modified it in order to accept and evolve more than two Proca complex fields. And obviously, we call it multi-Proca torn. Okay, for the evolution equations, we use the standard BSSN scheme. So the metric is given with these expressions. And
10 minutes.
for the nth Proca field from the set of 12 plus 1, we have this system of evolution equations where we can find the three evolution equations for the three remaining fields I mentioned before, but also we can find an additional equation for this C variable. This C variable is an error field that is defined using these equations in order to damp the constraint violating modes that do not propagate away of the numerical grid. In electromagnetism, in Maxwell electromagnetism and in Proca electromagnetism, there is this modes with zero characteristic speed. So we need to define this additional field to damp these modes that violate the constraint, the Gauss constraint that is present here as well. So as the L equal to 1 is unavailable due to the physical analysis I mentioned before, we begin our study with L equal to 2. I mean for two Proca stars. And for this case, if we make the numbers, we will need 8, or we needed 8 dynamical variables to evolve this system using these equations, basically. Okay. So let me show you some of our first results. This plot here at right is the solution space for the L Proca star with different values of L. We focus, as I mentioned, in the case L equal to 2. So we first took the solution with the maximal total mass here. And after some time evolving in our cluster in Valencia, we saw that collapse to a black hole. We also took a more compact solution, and as we was expecting, this solution also collapsed to a black hole. In some stable bosonic stars, this branch at left used to be the unstable branch. So we were expecting that this solution will collapse. And the right branch used to be the stable branch, but in this case, it's not completely stable. When we took this solution, the solution migrates to a new configuration, losing the spherical symmetry. In that sense, this is consistent with the previous studies of zero Proca stars. And to see that loss of spherical symmetry, I want to show you some gift about the evolution of these systems. First, I want to explain the first row. These plots here are the XZ plane of the scalar fields for m equal to 0, 1, and 2, and they are coupled gravitationally, forming, as I explained before, a distribution that has spherical symmetry. As we can see here in the bottom, we can see two planes, XZ plane and XY plane of the energy density at the time equal to 0. Okay, and when we begin the evolution, we can see them oscillating due to this complex phase that has this time harmonic dependency. The spherical symmetry of the distribution looks well, but at more or less 600 in time, begin to lose that spherical shape, begin to show this more or less toroidal structure. I'm going to show a frame, a specific frame of the final time. For example, if we analyze here in the scalar fields, we can see that the scalar potential for m equal to 0 lose the initial shape that is given by this form. The other scalar potential for the other values of n more or less are the same. In this case, they look more dilute, but are the same with the same shape. And in the case of the energy density, if we extrapolate these two planes, we could imagine a shape of a square-like shape toroidal, more or less. And that was something that worried us because this square
5 minutes.
shape could be associated with the Cartesian coordinates of the Einstein toolkit grid. So to try to understand more what is happening here, we performed a Fourier decomposition in the azimuthal modes of the energy density. And we have these azimuthal modes for m equal to 1 to 4. And we could see that from the beginning, the m equal 4 mode begins with a value different from 0 and different from the other modes that are coupled, basically. The 1, 2, and 3 are modes that are coupled. And then the m equal 4 mode saturate all the evolution with 2 orders of magnitude above the other modes. Okay, the presence of this m equal 4 mode could be associated, as I mentioned, to the Cartesian numerical grid, but could also be related to the physical of the system. That's something that we are analyzing now, and we try to understand better. One of the things that we are doing to try to understand better this is, for example, using another approach. Propose the dynamical formation using Proca fields, dilute Proca fields that we are calling them as Proca clouds, and try if in the formation that they show the same characteristics of the presence of this m equal to 4 mode, and see if it is what is the cause, something like that. So for that, what we did was take a method inspired in this paper for Silao and collaborators in 2015, where they study Schwarzschild black hole with vector hair, and they use this decomposition for the metric variables and the electromagnetic fields. They also consider a vector potential equal to 0, and the conformal part of the electric field they consider as a conservative field, so they introduce an auxiliary scalar potential here. Then with all of these considerations, they rewrite the Gauss constraint equation in this way as a equation of second order just in the radial derivative, and imposing two boundary conditions, they obtain analytical initial data for the matter content. What we did basically was to test our the implementation of our code for this Proca fields dynamical formation scenario. We first go with the case L equal to 0, M equal to 0, because there are already some studies with that case in the with the mechanism
2
scenario.
minutes.
So we try to analyze the case P equal to 1. That is a parameter that is presented here in the ansatz of the scalar field, the conformal part of the scalar field. The problem with this scalar field ansatz is that it's singular at the origin, as we can see, and also the electric field that we can compute from it has a constant value, similar as the case of the L equal to 1 Proca star that we were talking in the previous slide. But the thing is that for the study of Silao, as he was studying in the black hole space-time, the singularity given by this matter content at the origin wasn't a problem actually. Nevertheless, this solution that looks unphysical was also used by Herdeiro and collaborators to form a Proca star that migrates from spherical to
1 minute, please conclude.
So in this case, as we are looking for more physical systems, we change this parameter p equal to 1 to p2 minus 1, obtaining this scalar, conformal scalar potential that is regular at the origin and behaves well at the infinite. And given an electric field computed from this scalar potential also behaves well at the frontiers. So with this analytical ansatz, we obtain initial data for the metric functions using
30 seconds.
initial data
Conclude.
code written in the University of Valencia using the extended conformal flatness condition. And we put this initial data to our multiprocessor and in the Einstein toolkit. We found that all the solutions collapse or disperse. And we understand now that the reason comes from the fact that our vector potential was set to 0. Now I changed that. I put a vector potential different to 0, consistent with the equations of motion of Proca fields. And now we already have some results. Sadly, I won't show them here, but I hope that in the next talks I will be present those solutions. So just to summarize, basically what we did was enlarge the solution space for Proca stars, including multi-field solutions with a richer inner multipolar structure. We also found performing numerical relativistic simulation in 3D without imposing any symmetry that L Proca stars are unstable under non-spherical perturbations and lose their spherical morphology. We basically did that for case L equal to 2, but the case 0, L equal to 0 is already did, so we basically can generalize the result. And in order to find stable ground configurations of L Proca stars, we have begun to study of their dynamical conformation using L Proca clouds. The next steps of this PhD project will be include a non-zero vector potential in all the simulations of multi-field Proca clouds, begin the evolution of 1 and 2 Proca clouds, and try to reduce, if possible, the m equal 4 mode from the simulations of the 2 Proca stars, maybe including some spherical patch that I saw that are available in the Einstein toolkit code. So that's it. Thank you for your attention.
Yes. Yes, Barbara.
Thank you for the talk. It was very interesting. How are you comparing this or proposing this as a candidate for dark matter?
Sorry. Could you
She asked,
repeat, please?
how are you proposing this a candidate for dark matter?
For dark matter. Okay.
Dark matter.
Okay. Because I'm going to the introduction. In this case, as I understood well, the idea is if there exists a primordial dark vector boson present in the inflation scenario, due to this process, will be amplified from the vacuum fluctuation of the space of the matter content in that time. And there are a previous study of Gorgetto that I don't remember the authors, but Gorgetto basically considered theoretically and numerically studies to show that these Proca fields, these vector bosonic fields, will condensate into Proca stars and survive as dark matter. In this case, as these Proca fields, as I show you here, just interact well, this is the simplest model. We are considering fields, in this case, just interacting gravitationally. We expect that if there are other interaction between the fields, should be weak as we expect for dark matter. But obviously, this system could be more complicated, putting more terms in the interaction components of this ansatz for the Proca fields. I know that our studies about action field, for example, for dark matter, but in the case of Proca stars, we could not rule out the possibility of the existence of a photon with mass at the early universe. So if that exists, the idea is that it should exist these Proca fields in the universe, presenting as dark matter basically, or could be dark matter in any case. I don't know if I answered the question.
Yes, yes.
I have questions. First one is if this Proca field, you can find some sort of thermodynamical equation of state that describes the interior of your star. And the second question is by you more part complete this question, like if you know by what means, like what kind of process you can get a primordial Proca field and
Sorry, I couldn't hear well the question. Could you repeat, please?
Just say speak louder.
if you can
Okay.
find some sort of thermodynamical equation of state that describes the inside of your Proca star.
Did you hear that? Can you find some thermodynamic equation of state that describes the inside of your Proca star?
Yeah, I hear it. I'm thinking about it. Thermodynamation, yeah, these systems are basically studied at a temperature equal to 0. These are approximations. We were thinking about that, about the thermodynamical state of these systems. Maybe we could do, I'm not completely sure, but what I was talking with some fellows are that maybe we can study the thermodynamical statistic of the system to introduce a temperature. This could be difficult, but I think it could be possible. I think it could be possible. And the second question?
How a Proca field can be created.
The second question was how a Proca field can be created in the early universe.
How what?
How a Proca field can be
How I
created
broke a field?
in the early universe.
Okay, I don't have the precise detail of that, but what I know is that we, well, we basically have vacuum fluctuations of some primordial fields. I guess that, well, in that case, what we used to think is that should exist a primordial scalar field, and from that would create some primordial scalar bosons. But in this case, I'm not completely sure if I can answer that question, but the idea is if there exists some primordial fields in the universe, why we have to rule out the case of this nature could be a scalar or vectorial. In this case, basically, this is an hypothesis. Basically, I'm trying to say that if that exists, if that primordial field exists, could be formed Proca stars at the following times. But the exact precise mechanisms of formation at that time, at the origin, at the earliest stage of the universe, I couldn't answer now.
Okay, let's thank the speaker and move on to our next.
Okay, thank you very much.